Concurrent search structures, such as this B-link tree, are widely used in operating systems and databases. Formally verifying these algorithms is hard. Existing proofs are large, complex, and mostly on paper, verified only by hand. The main reason these proofs are hard is that the concurrency proof, that threads don't mess with each other's results, and the memory safety proof, that threads only read memory they're supposed to, are all intertwined. Luckily for us, it turns out that most search structures reuse a small set of general synchronization techniques, such as this link technique. Wouldn't it be great if we could verify a concurrent template proof once and for all, and instantiate the proof across many different data structure implementations? Then we'd have modular, simpler proofs that can be reused widely. Come to our talk to find out how.
Armada is a language and tool allowing developers to write high-performance concurrent programs and prove them correct. The main goal of Armada is to provide developers flexibility so that they can write whatever programs they want in service of that high performance. So we want to allow writing proofs about any structure of code, about any synchronization mechanism, or even no synchronization mechanism at all, such as they might use for a lock-free data structure library. We also strive for realism. We want these programs to run on real machines. So we only assume a weakly consistent memory model, specifically x86 TSM. Finally, we want to leverage automation to lower the burden on the developer. So our tool automatically generates proofs using only a modicum of developer guidance. I hope I've interested you in learning more about Armada, which you can do by coming to my talk on Wednesday at 11 a.m. You can also read the paper and download our code from GitHub. Thank you.
Suppose one wants to automatically verify the safety of some concurrent program. Assuming a finite data domain on the side of the program and sequential consistency on the side of the memory, this is conceptually trivial. Verification is reduced to state reachability in one big finite state system. But what if the memory provides weaker guarantees? In this work, we study this question for causal consistency, one of the classical models more liberal and thus more efficiently implementable than sequential consistency. Causal consistency appears in distributed data stores and also in multiprocessors and programming language memory models. Verification is now much more challenging. As an operational semantics, causal consistency is inherently infinite state. Whether a read can observe some value may depend on an unbounded execution history. To solve this problem, we develop a new lossy operational semantics for causal consistency that can be used in the framework of well-structured transition systems. If you want to learn more about this problem and the new semantics, you are welcome to watch our talk and check out our paper.
Verifying concurrent programs is notoriously difficult, since the programmer has to devise an inductive invariant that captures complex relationships of overlapping concurrent computations. This task is extremely tedious and error-prone. But suppose the programmer could just focus on a single sequential execution order, for example, where all protocol rounds execute one after another, and within each round, all actions execute in a fixed order. Clearly, the invariant becomes much simpler. But what's the point of verifying a single sequential execution? We present inductive sequentialization, a proof rule that establishes a sequential reduction that captures all behaviors of the original concurrent program. It uses proof artifacts that are themselves sequential in nature, and it embeds in a refinement methodology that allows us to provably derive fine-grained implementations. To learn this new secret shortcut to verify concurrent programs like a real distributed systems expert, come to my virtual talk, read our paper, and play with our verifier.